Welcome to this explainer. Today, we're going to dive into some seriously fascinating industrial mechanics that are literally hiding in plain sight within the objects we use every single day. I mean, have you ever really stopped to think about how the metal shapes around you are actually made? Today, we're going to unpack exactly how this manufacturing works right at the fundamental level. Think about it. How on earth does a flat, super rigid piece of metal turn into that seamless soda can sitting on your desk right now, without just snapping into a million pieces? It kind of feels like magic when you consider how incredibly tough metal is. You can't exactly stretch it out with your hands like pizza dough, and yet millions of perfectly seamless, structurally sound metal objects are pumped out of factories every single day. So how does the industry actually pull this off?
Well, here's our roadmap for today's explainer. We'll start with a quick welcome to sheet metal working, lay down the rules of the metal, look at the three major forming processes, and finally, unpack the art and the exact stages of deep drawing.
All right, Section 1, welcome to sheet metal working. Let's cover the basics. Before we get into any of those complex 3D shapes, we need to talk about the material in its simplest form.
So, sheet metal working is basically the industry's umbrella term for cutting and forming operations performed on relatively thin sheets of metal. But notice those words, relatively thin. In engineering, precision is everything, right? We can't just leave a definition at something as vague as relatively thin. We absolutely need strict parameters.
Which brings us to Section 2, the rules of the metal. What exactly qualifies as relatively thin out in the industrial world?
The magic number you really need to remember here is exactly 6 millimeters. This single measurement acts as a hard boundary in the manufacturing world. It dictates what machines you use, how the metal is going to behave, and honestly, what we even call the material itself.
To put that into perspective for a second, if your metal thickness is anywhere between 0.4 and 6 millimeters, boom, it qualifies as sheet metal. Anything thinner than 0.4 millimeters is generally just considered foil. But the very second that metal crosses the 6 millimeter threshold, it plays by completely different rules and gets a new name: plate metal. You definitely wouldn't use sheet metal to build a heavy bridge support, and you wouldn't use plate metal to stamp out the hood of your car. For today, our focus is staying strictly inside that 0.4 to 6 millimeter sweet spot.
Now, here's a real plot twist. Shaping this sheet metal doesn't actually require a raging furnace. When most of us imagine metalworking, we immediately picture glowing orange steel and sparks flying everywhere, right? But surprisingly, the processing of sheet metal is usually done right at room temperature. It's an incredibly efficient industrial method known as cold working. And by keeping the metal cool, manufacturers actually maintain way better control over the final dimensions, and they end up with much stronger parts in the end.
To achieve this cold working, they use these massive, powerful machines called stamping presses, and that's a very specific term to separate them from the presses you'd use for something like forging or extrusion. Stamping presses use raw, unadulterated mechanical or hydraulic force to punch, bend, and shape that cold metal, literally in the blink of an eye.
Moving right along to Section 3, the three major forming processes. Now that we know what the metal is and the machines used to process it, let's explore the three primary ways we actually manipulate it. The actual tooling, doing all the heavy lifting inside those massive presses, is called a punch and die. You can think of the punch as the moving part that delivers all the force, and the die as the stationary mold underneath that catches the metal. The final products that pop out of this whole operation are, logically enough, called stampings.
Now, the work performed by these stamping dies cleanly breaks down into three major categories: drawing, bending, and cutting. Honestly, almost every single piece of sheet metal you encounter in your daily life has gone through at least one, if not all three, of these exact actions.
Let's make sure we're totally clear on the differences here. Cutting is exactly what it sounds like, separating big sheets into smaller pieces or punching out holes. But bending and drawing, that's where the magic happens. That's where flat metal is practically coerced into complex three-dimensional shapes. Basically, cutting changes the boundaries, but bending and drawing completely rewrite the fundamental geometry of the material.
All right, Section 4, the art of deep drawing. We're going to focus entirely on drawing right now, specifically deep drawing, because this is what results in those amazing seamless objects in your home.
Think about the journey here. We start with a simple, completely flat circular blank, and then it gets systematically forced through multiple stages of drawing. It turns into a short, wide cup, then a narrower, taller cup, until finally it transforms into an iconic, seamless beverage can. The crazy part? The metal isn't being cut and welded together to make that shape. It is literally being stretched and flowed into it.
And this mind-bending process isn't just for holding your favorite soda. This specific drawing process is responsible for your perfectly smooth stainless steel kitchen sinks, those heavy-duty pots and pans you cook with, and, believe it or not, the massive automotive fuel tank sitting inside your car. It is a highly scalable process that is absolutely foundational to modern manufacturing.
So let's pin down a formal definition. Technically speaking, this transformation is called deep drawing. It's defined as the process where a punch forces that flat sheet metal blank directly into a die cavity to make cylindrical or box shapes. The metal is quite literally drawn down into the void of the die.
Finally, Section 5, Stages of Deep Drawing. To really understand this step by step, we need to slow time way down and look at the actual physics at play.
Imagine freezing the stamping press mid-strike. You've got that intense downward force of the central punch hurtling toward the sheet metal, which engineers call the work, pushing it down into the die cavity. But here's the clever part. There's a specialized component called a blank holder that clamps down super tightly on the outer edges. Why? To keep the metal from wrinkling up as it gets violently pulled inward.
All of this happens in just a fraction of a single second, but it's an incredibly intense, rapid-fire sequence. Stage 1. The punch makes its initial high-impact contact with the flat metal. Stage 2, bending happens, as the metal is forced right over the hard edge of the die opening. And then Stage 3, straightening. That newly bent metal is instantly pulled down straight alongside the vertical walls of the descending punch.
Finally, as that punch drives even deeper, the metal is subjected to extreme friction and compression. Because material is being dragged all the way from the outer edges to form those new vertical sides, it creates huge internal stress. And this violent stretching actually causes the newly formed walls to physically thin out. So while the bottom of the cup keeps its original thickness, the walls are stretched thin to reach that final shape. It is just an absolute masterclass in physics and engineering happening entirely at room temperature, thousands of times an hour. So, as we wrap up this explainer, take a quick look around your room right now. Every single seamless can, pot, or sink you see is hiding this incredibly intense history of industrial deep drawing. It really makes you wonder, doesn't it? What other invisible, everyday physics are holding our modern world together?